Hello dear students. In last lecture we have discussed about the basic concept and definitions about the microscopy. Now we will move towards the what are the important things which we have to know about the how the microscope or how the image formation is carried out by means of these are different dependent factors. So here we will discuss about the numerical aperture. So here aperture is nothing but a hole and numerical is nothing but numerical value you can see. So here the numerical aperture of a microscope or microscopic objective is a measure, that is measurement of that aperture of its ability, that means the ability of that microscope or that aperture to gather light and resolve fine specimen detail at a fixed object distance through a specific media, that is either air as a medium, water as a medium, or immersion oil, or we can say oil immersion as a medium. So it is nothing but a capacity, or we can say the ability of a microscopic microscope objective to collect or gather the light which is passing from that diaphragm, which is passing through the objective and now enter into the numerical aperture. So it is nothing but the ability of the numerical microscopic object to collect or gather that light and resolve fine specimen detail at a fixed object distance, and after proper adjusting of that fine adjustment knob, we can resolve the proper structure of that particular objective which is we have to fix or place on the stage of your microscope. So it is nothing but the ability of that objective, so that we can define a clear image of that particular object. So numerical aperture value, or we can say numerical aperture, is also depend upon what type of medium or in which medium we are observing our object, or where we are performing your microscopy. Either air medium, so here air has its separate numerical value, numerical aperture value. In case of water medium, or we have placed a water drop, so it also shows another numerical aperture value. In case of immersion oil, we can also observe another numerical aperture value. So numerical aperture of a microscopic objective or microscope objective can be calculated by means of, that is Na is nothing but a numerical aperture, which stands for Na numerical aperture. It is nothing but is equal to n into bracket sin theta. So by using that formula, we can calculate the numerical aperture value of your objective of your microscope. So it is a formula which can use to calculate the numerical aperture value of your microscope. Where n, that means that is small n, it is nothing but a refractive index of the medium. In last lecture we have already discussed about the refractive index, and it depends upon the which type of medium it is. So n, or that n which is present in the numerical aperture value, that is small n, it is nothing but the value of the refractive index of the medium, and it should be between 1 to 1.5. So which type of medium is we are observing our object. So depending upon the ability or the refractive index of your medium, that n value can also affect. As n value is affected, numerical aperture value can be also affected. So here theta, that is nothing but a sin is nothing but a trigonometric terminology, and theta is nothing but a the half angle of the cone of light entering an objective as known as theta. So it is nothing but an angle where that light is passing through an objective or condenser, and now between the objective lens and the condenser you have placed your object, and the light which is entering into the objective, and that cone of light is formed. So it is nothing but a half of the cone of that light angle which is entering into the objective, and that half angle is nothing but called as theta. So depending upon what type of angle it is forming here, we can place your value. In the case of sin theta, we can say if that angle is nothing but 60, the cone which is forming at the objective lens, it is nothing but 60 angle. So it is nothing but a half of that angle. So we can say it is nothing but a sin theta, means sin 30. So we can use sin 30's value and put your value in that bracket and multiply by refractive index of that medium. We can count your numerical aperture value. So here, when imaging through a air, then n equal to, that is equal to the refractive index of the air, it is nothing but a 1. And numerical aperture depend solely on the sine of theta, which theoretically can be maximum 1, where sine 90 or sine 90's value is equal to 1. So as we have discussed earlier, when we use 60 value, numerical aperture value again become lower down. So we require sine 90's value of theta angle at least 90, so that we can observe your numerical aperture value at least 1. In practice, it is difficult to achieve numerical aperture value which is greater than 0.95. When we observe our microscope, in case of air media, we highest observe or we can achieve numerical aperture value at least higher 0.95. More than 0.95 we could not achieve numerical aperture value. To resolve your specimen more nicely, we require higher value of your numerical aperture. That is nothing but a cone of light entering into the objective lens, or we can say it is nothing but a half angle. So that proper light which is passing through that objective should be entered into the objective, so that your objective can be resolved, or we can define that object clearly. That image can be formed at the eyepiece end, so that we require higher numerical value. In case of air medium, highest value we can achieve it is nothing but a 0.95. To achieve higher numerical aperture value, different medium can be used, so that with dry microscopy, here we can achieve highest value, that is 0.95. In case of dry microscopy without any medium, that is through a air. Hence, many microscope objective, that is high magnification, there we can use to achieve higher magnification. Many microscope are used, different medium are designed to use with a liquid paraffin, which is nothing but we can use as a medium where that light is passing from. At the place of above the objective, we can place liquid paraffin, which is having a refractive index values 1.4. Another we can use glycerin, which is having refractive index value 1.47, and another nothing but a immersion oil, or we can say the cedarwood oil, and it has refractive index value, that is 1.51. So normally highest refractive index value of cedarwood oil or oil immersion you can see or observe, that is 1.51. And if we place that particular 1.51 value at the place of n, we can achieve higher numerical aperture value or that angle, so that you can resolve your specimen with very nicely, so that many of the microscopy or to achieve higher magnification, when we observe our object under oil immersion objective, or we can say 100x microscope, we normally use oil immersion, or that objective is also called as oil immersion objective. And at the place of that object and the distance between objective lens, we place a cedarwood oil drop, so that that light passing through that objective can enter or pass through that objective, and all the light can be gathered into that oil immersion drop and now enter into the objective. Without scattering of that light, they are directly enter into the objective lens, so that your specimen can be highly resolved, or you can achieve highest magnification. So it is nothing but a numerical value, and you can calculate by using formula. Numerical aperture is with the n into bracket sin theta, where n is nothing but the refractive index of your medium, and sin theta is nothing but a half of the angle of cone of light which is entering into the objective. So depending upon which type of medium you are using, numerical aperture value can be varied. So here another term, that is angular aperture. So it is the angle of cone of light that can enter the lens. It is nothing but an angle of cone of light which is entering into the lens, that is nothing but the objective lens, and that is called as angular aperture. So here we can see it is nothing but a slide, and we have fixed your smear here, either with the help of cover slip, or that objective is uncovered. So that distance, it is nothing but your objective lens, and that distance between objective and objective lens, here that light is passing from that objective, which is emitted from the light source, And as the light enter into the objective lens, that complete angle which is formed, it is nothing but angle of light, and we can use only half of the cone of that light which is formed or which is entering into the objective lens, and that half angle is called as sin theta. So it is nothing but a value which we will use in case of calculating numerical aperture, and it is the half the value of that cone of that light. So it is nothing but a numerical aperture. In this diagram you can see, as we place a cedarwood oil or oil emulsion, here the all light is entering into the objective without scattering of light, and that's why that angle your objective can be magnified better as compared to the dry medium. Another is resolving power. So it is nothing but a how the object can be resolved or we can achieve higher magnification. It is defined as the ability of a lens to distinguish between two particles situated very closely. When we talk about the microscopy, we use microscopy to distinguish or to observe a small type of microorganisms with the help of microscope, either or we can magnify up to 100 or we can say 1000 times of that particular actual size. So as they are very small in size, they appear very closely. So by using resolving power, we can assume that though they are situated very closely, but they appear as they are separated from one another. So that is the ability, and that definition in case of resolving power we can say is nothing but the ability of a lens to distinguish between two particles. We can say it as two small dots situated very closely, but they are appearing as a separate, or we can distinguish from them from one another. So it is nothing but a resolving power. Resolving power of the objective lens is measured by its ability to differentiate two lines or point in an object. It is nothing but a ability of the objective lens to differentiate two lines, or we can say it is nothing but a points in an object, so that we can differentiate it with one another. Resolving power is also depend upon numerical aperture. So as your numerical aperture value is more, your resolving power can be more, as respect to we can resolve specific objective very nicely, or we can observe the particular distance or differentiate one small dot from one another, or we can say small organism you can see very nicely. So resolving power of your objective is also dependent on the value of numerical aperture. Larger the numerical aperture, the higher the resolving power. As numerical aperture value is more, your resolving power is more. Here, resolving power you can calculate by using d equal to 0.5 lambda upon n sin theta. So n sin theta is nothing but a value of numerical aperture. 0.5 is nothing but a constant, and lambda is nothing but the wavelength of your light. So you can say lambda upon Na is nothing but a numerical aperture of your objective plus numerical aperture of your condenser. So by using or calculating the numerical aperture value of your condenser and your objective, we have to place your value of that particular numerical value at a particular formula, and at the place of wavelength we can say d is nothing but the resolving power in that formula. Lambda is nothing but the wavelength of light, which type of light we are using, and what is the wavelength of that light we have to place here. And by calculating the numerical aperture value of your objective and condenser, you can calculate or place your value, and by calculating that value, you can calculate the resolving power of your objective or your lens. So n is nothing but the refractive index of the medium, and n is nothing but the numerical aperture, which we have already discussed. So it is nothing but the ability of lens to differentiate two small points as they are very closely situated. We have to observe them very nicely. Now we will discuss about the working distance. It is again another term. It is a distance between the front lens of the objective and the object on the slide when in a sharp focus. So it is nothing but the distance between the center point of your objective lens or the it is nothing but a front lens of your objective lens and your objective. So that distance is called as working distance. So here we can see it is nothing but objective lens, and from here to here it is nothing but called as working distance. So working distance we can calculate by two ways. It is different for covered and uncovered object. So here covered object, that is nothing but the your objective, your smear is covered by means of cover slip, and uncovered, that is that smear is not uncovered, covered with the cover slip. So that working distance can be varied with respect to covered and uncovered object. So working distance of uncovered object, that is it is not covered with the cover slip. It is calculated by counting the number of turns of the micrometer screw, that is the fine adjustment knob, required to raise the objective from a surface of slide to a point where microscope is in sharp focus. So by using a rough adjustment, you can focus your point or objective at a particular point where you can observe your slide, and by using this fine adjustment knob, you can focus your slide very sharply, and at here how much turns of the sharp or fine adjustment knob we have screw, we have count that turn, and where that objective is in the sharp focus, it is nothing but the calculated by using that formula. For example, turn of a micrometer screw, that is the fine adjustment knob, that is 0.1 mm, and number of turn required to bring object in a sharp focus, that means to clear your object with sharp, or you can observe sharp image, we turn your sharp objective knob at 8 turns we have used, so we can calculate the 8 turns, and here therefore the working distance is 0.1 into 8. At 1.1 is nothing but how much type of distance between working distance can be varied by moving that screw of your fine adjustment knob. So we have considered as nothing but 0.1 mm, and 8 turns we have evolved your fine adjustment knob. So 8 into 0.1. So in case of uncovered object, it is nothing but working distance of that object is nothing but 0.8 mm. So in case of covered object, so here the distance may be vary as cover width of the cover slip can be minimized. So here it is the objective or specimen is covered with the cover slip. The free distance will be less as compared to the uncovered object. It is determined by counting the number of complete turns of a micrometer screw required to raise the objective from a surface of a cover slip to a point where objective is in a sharp focus. So here we have also considered it nothing but one turn with nothing but 0.1 mm, and we required 3.5 turn to focus your objective at a sharp focus. So 0.1 into 3.5 we can count, it is nothing but 0.35 mm, it is nothing but working distance of your covered object. So by assuming that it is nothing but here 0.35, and in that case we have observed 0.8, it is nothing but 4.5 distance, it is nothing but width of nothing but the cover. So by calculating or placing that particular value, you can count the particular working distance of that object. Here another part is nothing but a ocular lens, or you can say it is nothing but an eyepiece. It is attached to the upper portion of body tube, contain usually two lenses. Upper lens, that is magnifier, while lower lens it is called as the field lens. So at the end of your microscope, at the upper position, you can observe your image of the your object. So that lens is called as, can be removable. That lens is called as ocular lens, or you can say nothing but an eyepiece. You can observe that eyepiece from 5x, 10x, 15x to 20x. So depending upon which type of lens we are using, that microscope, that eyepiece which is loaded at the end of the eyepiece. So upper lens is nothing but called as magnifier, while lower lens is called as field lens. It magnifies the image produced by an objective and are available with 1x, 2x, 5x, 10x, 15x and 20x magnification. That eyepiece can be removable. Upper part can be removed. We can clean that glass, and the upper glass is called nothing but a magnifier. Total magnification obtained by compound microscope is product of the magnification obtained by the objective and ocular lens. So here ocular lens has following function. It is nothing but when we have observed 15x using eyepiece at the upper ocular lens, and your objective lens we are observing under 10x, so 15 into 10 we can, it is nothing but a 150 150x your magnification. So it is nothing but a multiplication of the magnification power of your eyepiece and objective lens. Ocular lens has a following function: we need to magnify the real image of a specimen produced by the objective. So it magnifies the real image which is produced by the image of specimen produced by the objective. It corrects some defect or distortion produced by the objective, and images, cross hair, scales, etc. So by using that eyepiece lens, we can magnify your image. So these are the basic functions and parts of your compound microscope, and these are the different definitions and how we can calculate the distance between what is meant by refractive index, what is meant by oil immersion, or what is the angle of sin theta, numerical aperture, what is meant by resolving power, and working distance. So calculating that particular formula or using that particular value of your image into that particular formula, we can calculate these different values, and these are very helpful to work more efficiently with microscope. Thank you. Next part we will discuss